because or in other presentation I asked specialist speakers, there are no waves, there are no waves, there are waves and just waves in the present presentation, and there are no crashing. The ice behave elastically. If you prefer to say that okay, it's not ice, it's elastic plate floating on water, it's fine with me. So ice, we can say just for simplicity. There's nothing special about ice. So the ice is modeled as an elastic plate of infinite extent, and there is a cylinder mounted on the bottom. Water is of finite depth, and that cylinder, no, ice, or okay, let's say ice, is clamped to that cylinder. And we want to know what's happening with the ice due to that cylinder. So there are three. There are three authors. That's me, University of East Anglia, and Malenica from Bureau Veritas. Actually, initiated this research, and Tatiana Khabakhpasheva, who was driving force, as always. Yeah, so this is the particular situations we study. It's legs of or piles of bases or offshore structures frozen in ice. So ice is finite, constant thickness. So there could be waves coming from infinity far field to that legs. Either there could be like shown over here, explosion. So these people, they put explosion over here to break ice. There could be also vibrator. There are some devices which, once you place on ice, they vibrate, generate waves, and if you manage with that waves, you can accumulate these waves in one point and break the ice in particular. So that is the new. It's in the north of Black Sea, and you see again that there is the piles. So actually, it's circular cylinders and ice. So the ice, they are frozen in ice. Either it's floating, not floating actually, but platforms like that one. Is it from that is from Gazprom, and that is could be also. And the both of them, they are, I believe, over there, so very north. And we are concerned, that is the what the people who are operating with this platform put online. We are concerned in particular what's happening over here and what's the effect of, say, contact condition between ice and columns. So we were involved in that from 2003. Actually, first kind of paper was published again with Malenica. It's the diffraction by vertical cylinder in partly frozen ice. So it was circular piece of piece of ice and the cylinder in between, and we were concerned with a diffraction of wave which come from the free surface on that ice and cylinder. Then, together with Emilian, we supervised Paul Berkeley-Hurst, and he solved the problem of the ice clamped to the vertical wall. So this two-dimensional problem, and it's published 2010. Then ice clamped to the vertical cylinder. So actually, in this presentation, I will repeat this solution, but kind of revisited the solution of that problem. And also, we are thinking about to generalize this analysis to shapes, to the cylinders which are not circular. And it's possible, and this year we published a paper with Nazile Dishibuyuk. She should be here, she will come later today, and she defended her PhD on this topic in this September. And so we are going to continue with that. The idea why the cylinders complicated shapes could be important is that once that cylinder are frozen in ice, any corner points at the cylinder, they're a point of concentration of stresses. And we can use these points to break the ice if needed. Right? So then we can design the platform legs, which are not circular, but with a special shape, could be with a star shape or something, such that we can easily disconnect the ice from that platform. And then Paul did, there are several slides about the dissertation by Paul Berkelhorst. Paul did a two-dimensional problem of incident wave propagating along the ice sheet towards the wall, and the ice is clumped at that point. It's he did also the two-layer problem, and he solved the problem of loads moving along the ice sheet in the presence of vertical boundaries, and some results from his dissertation. Nice picture. I cannot do like this, so that is the only one a colored picture in this presentation. And interesting about the cylinders frozen in ice, and something which makes the problem very particular, is that in waves there are vertical force acting on ice or acting on cylinder. If the cylinder is in open water, there are no vertical force on it, right? But in ice there is, because there is a shear force on that contact line, and this force is very large. And from design point of view, I believe it's very important, because if your structure goes upside down, up and down, then the contact with the bottom, it could be broken. And this is much worse than the horizontal motion of the structure. As to the horizontal force, it's shown over here. Okay, as expected, B is the radius of the cylinder. If the cylinder is bigger, then the force is bigger. But all that forces, with ice, they are below of green line, or blue line, which is for the free surface. So presence of ice reduces the forces, horizontal forces. On the other hand, it gives rise to vertical force, right? So it's another physics, another design. And also, if you look at if you look at that this picture, you can find that the ice should be thickness of ice should be really small, few centimeters, to model, or to forget about ice, to model it as a free surface. But it's possible. So everything is in that paper. Then others, like Tkacheva, she did a problem for finite length of the plate, elastic plate, frozen to the vertical wall. Then Soares and his students solved the problem, the same problem as we did in two-dimensional case. However, they use the vertical modes. So actually, we will use the technique in particular. We will use the technique from that paper to solve our problem and to generalize it to more complicated shapes. Also, in this paper, it's 2014, already the two-layer fluid and finite elastic plate, so there are more and more complicated configurations were published from that time. Okay, some nice pictures from a PhD dissertation by Paul. It's a load moving along the wall, and depending on the distance from the wall, the stresses and deflections are different, and also you can see the waves between the direction of the motion and the wall, so the kind of standing waves. So there is something, so the presence of wall is quite important. Also, during the second workshop, there was a presentation by Tatiana Khabakhpasheva, that one, and with Konstantin Shishmayov. He should be here. No? It could be not well. It's about waves propagating inside the channel. And that is it's very close problem, because in that problem also there is the ice sheet, but that ice sheet is finite width, and it's clamped to the two vertical walls. and that walls are important, and the idea is to not help, but to account for the presence of vertical walls in the ice tank. All ice tanks are finite width, but in reality we are thinking about the sea ice condition, so it's ice of infinite extent. So if we found, and actually it's happening, okay, at least theoretically, if we found that the presence of walls change the conditions, change the stresses significantly in the experiment compared with the infinite ice, and computation based on ice of infinite extent, then we could be in trouble. And actually, indeed, it's happening. So we are working with at least one ice tank. We ask them to give us results, their result measurements, and we are going to simulate that results and to estimate the effect of side walls. So, and that is the recent results by Shishmarov. He just arrived. It's about the motion not in the central line on the channel, but closer to one of the wall, and you can see that if the something moving very close to the wall, there is a concentration of strains at the wall. So it's likely the presence of vertical walls, presence of contact lines between the structure and ice, it gives the places of strain concentration. It's likely that ice is broken there, but not in open places. So that is the formulation of the problem of the present presentation. So it's just the same as we did several years ago with the million per hour and Paul Berkeley-Hurst. So the water of finite depth and cylinder of radius b, and the ice sheet is of infinite extent and constant thickness. There is the incident wave, which is with wave number k and frequency omega, and k and omega are related by dispersion relation, so standard dispersion relation for floating elastic plate. The difference, or what makes this problem is unusual, is that condition at the contact line over here. That condition, that is the clamped condition, and we need to incorporate that condition in our modeling, which could be not simple. And that is the simpler view of the sketch of the problem. So everything is shown. So the Laplace equation in the water, kinematic condition on the ice fluid interface, that is the elastic plate equation, and that is the condition on the contact line, and that is the dispersion relation. So that is the easy to understand, that the list of equations, I believe. Then, okay, let's continue. So first about the dispersion relation. And that dispersion relation we will use in that form, so just convenient for us with two parameter q and delta. In that parameters, you can see the omega is the frequency of incident wave, h is the water depth, LC is characteristic length of the ice sheet, and omega 0 is the frequency of floating ice. So if you put piece of ice on surface, it oscillates due to the buoyancy, the balance of buoyancy and gravity, and that is the frequency. So just we try to give name to each element of that dispersion relation in order to analyze it later. So that is the root of dispersion relation. And what's happening, the sum of the roots can collide. Some roots can be double, and some roots can be triple, and that is making problems, but we consider a regular case only. So, and then the same dispersion relation can be used for broken ice. We're just saying that there is no rigidity. So we neglect that term, and then we get the dispersion relation for broken ice without bending stiffness. If we, in addition to neglect the mass of floating ice, we set m equal to 0, then it will be equation for the water waves on surface, right? So working with the elastic plate, we can solve two more problems. I mean, with broken ice. And for broken ice, there are no condition on the contact line, because the broken ice is not connected. There are no connection with the cylinder. That is important. For free surface, it's the same story. No connection with the free surface. No connection with the cylinder. So the water surface can move freely in that sense. Okay, so but then because the diffraction of water waves on a circular cylinder is classical problem, it's textbook, so we should use that, right? Okay, we are using that, and that is the displacement of incident wave. That is the velocity potential of incident wave. And first of all, we are saying, okay, we solve the problem, but we are not going to account for the edge conditions. Right? So we just forget about that condition. We say, yeah, there are no such things like that condition, and it's possible. It's possible if we look for equation for the potential in the same form as the incident potential. However, that complex potential big phi now is unknown and should be determined, and the problem for that big phi is over here. And that is a standard problem, and it's solved in 50s by McCamey, and that is the solution. So it's given, so we do not need to do anything. However, now we can say that that is the solution was derived for water waves. However, now we can say that we can use this solution also for broken ice, because the difference between water waves and broken ice is just in dynamic, just in dispersion relation. That's all. Right? So if you neglect that term, and you can see the you can see. You can see that that phi is independent of the dispersion relation. There are nothing from the dispersion relation in this formulation. So this problem, this solution, just that one. So that function is solves three problems: water waves, broken ice, and elastic plate problem without that condition on the contact line. And if so, we can find the ratio between the amplitude of force acting on the cylinder in ice and on the free surface. And actually, it's just the difference, just the ratio of frequencies. We assume that we are comparing waves of the same wavelength. If so, we can find that parameter, and it's given by that. Here, that one, this term is about rigidity, and that one about inertia of floating ice. Right? And we can say rigidity increase the force, the horizontal force acting on the cylinder, and inertia always, it's plus here, always reduce the force. Right? And we can estimate, because for broken ice, that term should be neglected, and also the length of wave in broken ice, at least to use the thin layer or thin plate approximation, we need to assume that length of wave is larger than the thickness of ice in one another respect. Then we can find that this parameter is greater than 0.6. So the presence of ice, big ice, small ice, it can reduce the loads, but not more than 40 by 40%. So the maximum what it can do, the margin is 40%. Right? Then our problem. So that is from now on we work with continuous ice with elastic plate with rigidity, with proper rigidity. Sorry. So yeah. Oh, sorry. Oh yeah. Sorry. Yeah. So the complete potential is thought as that potential without account for edge conditions and plus correction potential. And the same we are doing with the displacement. So that is the displacement without account for edge conditions, condition at the contact line, and that is the correction. And it's convenient just to write that in this form, separating angular coordinate. And then for the function phi m and wm, we arrive at that equation, this equation. This is nothing else as a Laplace equation. That is the plate equation. That is the kinematic boundary condition. And now the condition at the contact line, they are written in this form. So if you look at that form, originally it was w equal to 0, w prime equal to 0. It was the clamped condition. Now it's another condition. It's still clamped, but it can move. And that is the problem of forced oscillation of the plate. So we take the contact line and move it up and down. Right? We generate the wave. So that is the problem. And that is the problem. Yeah, sorry. That is the problem. And to solve this problem, we use the David Abrahams is not here, I believe. But as far as I know, the first papers on this technique was by David Abrahams, our director of RNI, and Jane Lowry. Also, the Mike Malon, Luke Bennett, and David Evans, Dicky Porter contributed to that, working with the so-called vertical modes. So as to that vertical modes, what's possible to the idea is that by using that equation, by using the Laplace equation, we can express that biharmonic operator. Actually, it's a double or Laplace squared equation, Laplacian squared. We can express it as the fifth derivative of the potential. That is the idea. So, and then by using that, by using this condition and kinematic condition and the equation of the plate, we can write these two as one condition with respect to the potential. So we can eliminate the deflection from the boundary condition. That is the idea, not my idea, no. But in that condition, there are two parameters. It's already written in kind of non-dimensional variables because that delta and the q, the parameters, they appear in the dispersion relation. They will be everywhere. So they're just two parameters. Okay, and they are shown once again over here. H is the water depth. So if so, then we can separate in this formulation. In this formulation already angular coordinate have been separated. Now we can separate vertical coordinate. We can separate vertical coordinate. Actually, we use the what students study on the second year or first year at universities is method of separating variables. Nothing else. Separating variables means we write the solution as product of two functions. Each of them depends only on radial coordinate and on vertical coordinate. That's all. We substitute and then we derive two equations. Most important here that for vertical coordinate, that one, for function which depends on vertical coordinate, there are two proper conditions and we can solve them. Right? We can solve them, but these conditions are such that 0 always is a solution. So we need to find non-trivial solution. Means we need to find proper relation between the delta, q, and kappa. And that relation is nothing else. Again, not my result. But it's just dispersion relation. Right? If kappa is solution of the dispersion relation for given q and kappa, given delta and q, then this boundary value problem has the non-zero solution. And for radial function, that one, it satisfies this condition. Okay? Yeah. Then as to vertical modes, the solution of that equation, the second order equation, is not difficult to find. It's that one. It's that one. That is that kappa n, the roots of the dispersion relation. They are shown again over here. That function, vertical coordinates, they are such that they are orthogonal, but they are orthogonal in not trivial sense. And it will be shown that if we think in simplified about orthogonality in simplified way, then there are no chance to solve this problem. And so these functions, they are orthogonal, and product, that scalar product of these two functions, they denoted by Qn. Qn is shown over here, so as you can see, this is a rational function, so it's not difficult to calculate it, as all calculations are rather straightforward. And that is the, and this is the relation, this is the paternality condition in particular was used, heavily used by Evans and Porter in 2003. There is, okay, let me show next, yeah. So that is separating variables. This is the problem for vertical modes, and that is the problem for radial functions. Radial functions, once we know that kappa, they are given by Hankel functions. So they're very certain. Everything's certain. Right? There we use the special conditions for normalization of this function. We use that this derivative of vertical modes, it's equal to 1 at the ice fluid interface, and the derivative of the radial functions are equal. Derivatives of the radial function are equal to 1 on the cylinder. So that is the normalization. It's quite convenient. If so, then as always in method of separating variables, finally we just sum up all these products and we are saying that is the solution. Okay, it could be solution, could be part of the solution, could be not solution, who knows. Then from the kinematic conditions, the deflection is given by that formula, and once we substitute that potential into the condition on the surface of the cylinder that the fluid cannot penetrate the rigid surface, we got that this series should be 0. And it looks like if we now not more than first or second year at university calculus, we should say that the coefficients are 0. Okay? But it's not. It's not. First of all, these functions, they are not orthogonal, as I said, in normal sense. And second, nobody knows are they complete or not. Nobody knows. So they could be any. Even they are very simple functions, the usage of that function, they are not trivial at all, and it was the main problem in this analysis. So then we use the way of satisfying the boundary condition as it was suggested by Sarge 3 years ago. If you look at that point, this point is very special. That point is between the ice and cylinder. At that point, the solution is not continuous. If we calculate mixed derivative, let me show that derivative. If we calculate that derivative, d phi dr ddz, so it's a mixed derivative, right? If we calculate that derivative along the cylinder, it's equal to 0. Because d phi dr equal to 0 over here, and we differentiate along the surface, is equal to 0. If we differentiate the same function over here, it's not equal to 0. Right? Okay, it's a function itself, potential itself is continuous. First derivative, they are continuous, but second derivative is not. And then it makes a lot of trouble, but on the other hand, it helps to solve the problem. So, to satisfy this condition, we apply that orthogonality relation. So we are saying, yeah, this is the relation we should apply. In that relation, there is integral over the interval, over the depth. -1 corresponds to bottom, and 0 corresponds to ice fluid interface, but also there are non-integral terms which are about the values of these two functions on the ice fluid interface. Okay? Then we are saying, yeah, we calculate d phi dr is that derivative which in the condition on the surface of the cylinder, and that derivative should be 0. But because we are not, we know, actually, we're sure that the function is not continuous, function or its derivative, it's not continuous everywhere in the interval, so we proceed carefully. Carefully means we satisfy boundary condition by calculating the solution or derivatives inside the region and then going to limit to the boundary, right? So this is the way to understand the boundary condition and satisfy the boundary condition. In many cases, we do not need such complications, such formalities, because everything is fine, but not in this problem. So we calculate that derivative, but we calculated certain distance from the cylinder and then goes to cylinder, surface to the cylinder. And if so, we use the representation, series representation, that series representation for the potential through the products. And we calculate that the that coefficient multiplied by that another values which quantities we already evaluated is equal to the limit. Also, we can calculate that limit. This is what's suggested. This is the way suggested by Soares. Is we can calculate by definition. If by definition we need to integrate that derivative along the underwater part of the cylinder, which is 0, then there is that part. Actually, it's proportional to the shear force at the contact line. And we are saying we do not know it, and we denote it as GH and other parameters, other factors they here for convenience. Then, as to that one, we are saying that is 0. That is 0 as over here. So then we are equating these two and saying GM is something we need to determine. We find the coefficient Cn, and they are given like this. It's mistake. Sorry, it's mistake. It's a GM. So means that 1 GM is for all indexes n, and n is is for roots of dispersion relation. Okay, so sorry, mistake. Then finally, the solution is that one. So that is the deflection. This is the radial function, that is the some quantities we calculated, and that is the velocity potential. So it's quite simple. A GM is calculated from the condition on the wall, or in the contact line, 1 equal to 1, when it's equal to 1. And we substitute R equal to B. B means that on the surface of the cylinder, and we calculate that coefficient GM is given by that formula. Right? However, there are two conditions. So there are surprises on each step. So it took long time to go through all that surprises. There is another condition, and that condition require that this series is 0. And nobody knows why. Why it's so? It could be that. It could be with something in numerator. Why it's so? However, by using the it's not shown here. So by using the results by or techniques by Evans and Porter and Luke Bennett, we can construct special function like that. And by using contour integration and residue theorem, we can prove that indeed that is equal to 0. But that is not the only condition. Okay, for this problem, this is the only condition, and that is finally, if we prove that it's the case, so that is the complete solution. So the obtained solution is given by series, which satisfies all equations of the problem. The series converge absolutely. So the convergence is very good. And in addition, that function, because they are given by the Hanke function are involved, they for the roots, for that roots, all these functions, they decay exponentially. Okay. So, but what we did, by using the separating variables, we constructed that solution. Then we substituted that solution in all equations. And we check that all the series, they converge, and all equations are satisfied. So we check the solution by substitution. However, there is a problem. There is not the end. There is a problem. First of all, as I said, that these roots can be double roots. Some of them could be triple roots. As to vertical modes, vertical modes, they are written for each root. If the root is double, what to do? I don't know. If it's triple root, what to do? I don't know. Because everything is based on the idea that the case is regular. So each root is a single multiplicity. If it's not, no idea what to do. But there is another way, and actually this is the reason why we did that way several years ago. It's the solution by Weber integral transform. So that is a different solution, a different way of solving. And also there is the as to that solution, there is another not good point about that solution. That solution can be used, can be applied this way. This procedure can be applied only to the problems with homogeneous boundary conditions. So no extra pressures are allowed. Nothing can be moved on ice. Nothing can be placed on ice. It doesn't work. Okay? So as to that one, by integral transform, it's better in some sense, but it's more complicated. However, we start from the same, this is the solutions without account for edge conditions, that is the corrections, and this is the formulation of the problem, the same as we did. And also we separate the angular coordinate because the cylinder is of circular cross-section, and then we use the Weber transform. Weber transform is rather complicated things like that. The kernel of that transform is that M is shown over here. That is a combination of functions. This is a special transform to solve problem for circular cylinders. The B over here is the radius of circular cylinder. Right? Integral from B to infinity, and in inverse transform, again it's S is real from 0 to infinity. So it's specially designed or good for circular cylinders. And but still problem because as you can see, this transformation can be used only if the function we transform then they decay quickly. But our function, they didn't decay so quickly. Our function represents the outgoing waves. They decay as 1 over square root of r, and so you cannot apply this transform to that function. So to find the way, we separate the outgoing waves, that one, with unknown coefficient, and we solve problem for evanescent part of the solution, and it's solved in that paper. So I can skip main part of that. So we are applying the transform to the equations, to the equation of the phase surface, to the ice surface equation in the fluid, starting from the surface of the cylinder to the infinity, and finally we arrive at the image of the deflection. It's given like that. So we solve it. We solve everything, and we are saying that we found that the image after the Weber transform of the deflection is given by the rational rational function. That one? No, not rational. No, but two functions, and R over here is the dispersion relation. Okay, function from the dispersion relation R. And then once we calculated the image, we can apply inverse transform, and then we use the result from that paper, Newman, who showed that that integral can be turned to imaginary part of that kind of beta integral. What's good about this integral is that the derivative of Hankin function has no zeros. So zeros for this function comes only from zeros of the dispersion relation. Right? And if so, we use the residue theorem and we arrive at the same solution. Okay? So, okay, it's not so short, but it's okay. Yeah? So the result is just the same. The point is that potentially, and this is what's done by our students, potentially we can calculate that integral. It's not so complicated. And we have no problem with double root, triple root. We have no problem with the condition of the free surface on the ice surface. However, that solution is more complicated, and if you apply the residue theorem, that series, they are well behaved, quickly converge, so you do not need the say 10, 20 terms. It's more than enough for main part of the condition. So the solutions are the same. So so we solve problem twice. And this is also not my idea, and it's not our idea. It's an idea from the paper by, I showed you, David Evans and Dickie Porter. Because they solve problem of hydroelastic wave diffraction by cracks, and they solve it problem twice by gain function and by vertical modes, because they were not sure about how that vertical modes works, because they are not complete functions, they could be not complete, nobody knows. They are not orthogonal, so they are something, but the gain function is a more reliable technique. However, the result is the same. So we did the same here. We solved the problem twice, and also we checked that solution by the vertical mode. We checked the solution by vertical mode. We checked that solution by substitution. So we straight substituted into the equation. Now, okay, we can if we have that solution, we can solve another problem. Why not? It's a free edge. So that part in that part we cut the ice from the cylinder. And we impose the condition that this is the VR is not exactly the shear force, but that is the right condition suggested by Kirchhoff. And MR is the bending stresses, radial bending stresses. They are all of them given over here. Actually, QR is the shear force, shear stress, shear force on the contact line. So that is two conditions. They are more complicated, but the solution is just the same. So we again introduce that correction function. We separate because it's circular geometry, we separate the angular coordinate over there, and then this condition, they give the Z2 equation with second and third derivative of the unknown function. So yeah. It's more complicated, but it's not so terrible. And then we use the separating variables technique again, and we do not repeat it because it has been done. So we write that series with a radial function and vertical modes. So it's everything the same. The problem is to find that coefficient Cn, and we use the same technique with the orthogonality condition, and we arrive at the coefficient, but now in contrast to the previous problem, the both terms, that one and this one, they are not zero, so we introduce two unknown functions gm and two unknown values gm and nu m, and the coefficient Cn over here, they are written like that. So you can see the n is the index of the summation over here, is only over there and only over here, right? And Qm and Gm in some sense constant in terms of the summation. So altogether the solution is given by this form where the function W1 and W2 depends only on the radial function and depends on the root of the dispersion relation. And it's not difficult to recognize that any solution of any problem is given in this form. Any solution of any problem, it doesn't matter what the boundary condition, edge condition will be on the contact line, it's just that one. So then you submit, you substitute that function in the boundary condition, these two, and you find the system of two equations for Gm nu m. That is the system to solve the sum coefficient, but the coefficient also can be calculated and we can solve. However, now we have three conditions of solvability. So it works only if this series is equal to that q. Q is the dispersion relation parameter. That series is 0 and that is 0. We show that that is 0. As to that one, okay, it was decided to check it numerically. Yeah. It could be possible to show, but on the other hand, if we calculate the root, this series depends only on the roots. So if that series is equal to 0, we find numerically, and that one equal to 0, we find it numerically, means that the roots we calculated, they are correct. And we calculated all the roots. all loads are there, and they calculated with good accuracy. Right? And the same about the first series. Yeah, okay, so now some numerical results. They will be shown, some of them will be shown, but actually it's not complicated everything what you want to compute. So that is the how to find the double roots of the dispersion relation. That is the dispersion relation. Then we differentiate this dispersion relation, equate the derivative 0, and solve this system with respect to Q and delta. It's not complicated, right? And we find Q and delta as function of kappa. And that will give us, so changing kappa, changing the parameter, we find the pairs on the plane Q delta, which provide double roots. And okay, the Q can be complex. It cannot be real. It proves that derivative is just greater than 0 if kappa is real. And if kappa is imaginary, then actually only on the imaginary axis the roots can be double. So these red lines, they give the positions or pairs that Q and delta. Each point of this line corresponds to double root of the dispersion relation, and that point. That one corresponds to triple root. Just one point. Some could say that condition could be not feasible. They are not physical. No, they are quite physical. To check, just one check I did. It's if we calculate the frequency of incident wave corresponding to this line and this line, and you can see that frequency is about 2 Hz. So it could be okay. I think it could be okay. It's not very exotic frequency. The practical solution I suggest, if we are on that line or at that point, we just make a short or say incremental step over here, and to solve problem without the difficulties. However, to solve the problem completely, it's better to understand what's happening with the double roots, and this could be a very special case, and could be not very special, not very unusual cases. So as to this series, the calculations were done with all roots were calculated with accuracy, as I remember, 10 minus 12. No, 12 to 10 minus 12, 12 minus 14, and z equal to 0 with accuracy, you see, it's very good, and that one is a little bit in trouble there, but still 10 minus 14, it's better than the accuracy we use for each root of the dispersion relation to calculate it. Then that is the radial strains at the contact line in polar coordinate. Means that is the different, these numbers is for different kh. K is the wave number and h is the water depth. And that is the column is for wavelengths of the incident wave in meters. So the O1 is very large, and you see that the strains are very small. If the incident wave becomes shorter, like 78, right? So it's 1.2. So then the strains are calculated as a radial coordinate from the center to the certain point, depending on angle. So the strains are always maximum at that position, and wave comes from the left. Wave comes from the left. So on the front side of the cylinder, the strains are maximum. So the limiting, yield strain for ice in this study was taken as 8 multiplied by 10 minus 5. Strains, maximum strains, 8, 10 minus 5. So then this means that for that wave, sorry. So all calculations were done with amplitude 1 centimeter, right? The problem is linear. So if it's 2 centimeters, then that value should be multiplied by 2, and definitely our ice will be broken at the front of the cylinder. Because the formally broken because the strain limit will be exceeded, right? But there is a problem. Okay, even for that one, it's about 5. If we the strain is about 5 units, say, and if we multiply by 2, it will be already 10, and the ice should be broken. But is it possible that the wave with length 94 meters and amplitude 2 centimeters it exists? Is it possible or not? Because it could be broken before. So the question is, that is very, I believe it's very valuable slide, but it's the most simple one. That is the incident wave. That is the strains in incident wave. That is amplitude of strains. Amplitude is proportional to thickness, proportional to the amplitude, and inverse proportional to wavelength squared. So that is the curvature, right? Curvature, to make it below 8, that one, and say for thickness 1.5 meters, so it looks like ice, and 94, the amplitude should be smaller than 2.4 centimeters. Yes, it's possible. It exists. It can come to the cylinder and break the ice close to the cylinder, but not before that. Another interesting, that is not the most interesting point on that slide. That is more interesting. We had many discussions about the nonlinear effects. Are they there or not? Huh? And now, but the nonlinearity parameter or parameter of linearization is a slope of wave. It's k multiplied by amplitude. And k multiplied by amplitude, the strain is proportional to thickness, and that parameter is inverse proportional to thickness. And that is strain is inverse proportional to length, but the amplitude, the linearization parameter is inverse, just proportional to length. Means that long waves and small thickness of ice, they are reason for nonlinear effects. And as the reference case, I took the 0.1 value. And indeed, it's possible for this thickness, if the length of wave is about, say, 100 meters, could be, I don't know, then it will be smaller than 0.1. Means for long wave, the nonlinear effects could be important and should be taken into account. And that is one slide for one result for solution of the problem with free edge of on the cylinder. That is something about the run-up effect. So the amplitude of the wave is 1 centimeter, but in the wave of 67 meters, the elevation of the ice on the cylinder is about 2.5 times greater than in wave. So it's a kind of run-up effect, but for ice. Okay. Okay. The non-circular cylinder can be solved. And there is some results. I just skip this slide, just explaining that it can be done. It can be done. It's some preliminary program of research is shown. So altogether, we need to solve many problems like this for each root of the dispersion relation. And after that, combine all of them. And finally, we arrive to integral equation at the contact line. And we need to solve that. Then the other problems which are quite possible to solve is there are no incident wave, but there is a vibrator sitting close to the cylinder and vibrating with certain frequency. Yeah, we can solve this problem. And the vibrator can be placed under the ice. And the problem is, as I said, on the contact line is the line of concentration of the strain, so we can break the contact line. Then the problem can be solved for several cylinders frozen in ice. Yeah, it's possible. And also for partly frozen ice. So over here the conditions are free, and over here it's clamped condition. So that is interesting problem with codimension 3 problem. So-called, there is even a special name for that problem. Yeah, and again, as I said, the nonlinear effects could be important, right? And if they are important, then it's very reasonable to solve two-dimensional, second-order problem. And that is formulation of the second-order problem. Could be not the complete formulation, because the equation of plate is still linear, but the nonlinear terms, they are always, you see, with that epsilon, and the epsilon is about that Ka, and if it's 0.1, we can solve the problem as by asymptotic analysis using the asymptotic analysis. So as it has been done as it has been done for water vase. So that is the conclusion. So some problem solved could be solved, and there is many problems to solve in future. Thank you.
Do you have these double roots if you remove inertia from the plate equations?
I don't know. We should check. Yeah, we should check.
I think that the plate inertia. So if you have broken ice, I don't understand at all why you need to count inertia if broken ice is floating.
Inertia.
It cannot add inertia if ice is floating. So then, why it should add inertia in addition to water inertia if each block is floating?
There are no water inertia on the free surface.
Yeah, that was some slide with counting. So
Yeah. So actually this means if we account for inertia altogether, but we are saying that the pieces are not connected to each other, so we just. Then this is broken ice. If we
you remove elasticity from broken ice, but still you keep additional inertia.
Yeah.
And that's my question. If each ice block is floating, how it may add additional inertia to the water? Because each piece of ice is floating, it has just exactly the same mass as mass of water removed by this block.
Yeah, I agree completely with this. I think this is really, I totally agree. Because you put 1,000 kilograms of ice in, but you've removed 1,000 kilograms of water. So they're just going to move, and it's not clear to me that they're going to behave very differently.
Yeah. So as it's here, it's indeed the inertia. There is another, if to speak about what the floating ice is doing, if you put on surface the rigid plate of the same density as water, it's change the flow.
Of course.
Right? It doesn't change if it's tiny.
No.
Yes, that is but it's not here. Yeah, it's only that mass, and actually it's small. Actually, it's small.
Because I think that inertia is the reason for this double roots, and I just finished very in 2 sentences. So, but inertia of ice, if it is solid, is important when ice mass is of the same order as water mass involved in the motion. If water is deep, so then effect with inertia could be ignored, because and wave is not very short. So then we should not have double roots. But if we have shallow water and we have thick ice, this effect may appear. But in that case, it would be very simple to study just shallow water approximation. And to avoid this infinite number of complex roots.
Yeah, that is the parameter. If you say the density of water and density of ice is about the same.
The same?
Yeah, one, right? Then the thickness of ice, if it's 10 centimeters indeed, but if it's 10 centimeters, there are almost no effects in terms of the load. However, if it's say 1 meter, 2 meters, And in that calculation, I showed the that one is, as I remember, 110.
Yeah, but then you should have very short wavelength.
No. The that parameter. That parameter. Just that one.
Okay.
Yeah.
But
That is additional. That is additional. Yeah. If it's short, yeah, that is the also can contribute. Yeah. But that one in calculations it was the H thickness depth. It was 15 meters and thickness of ice 1.5 meters. Yeah. But yeah, we can. Sure. So it's another question. Should we neglect?
but the wavelength is another parameter. So then,
Yes.
I mean, inertia is important when amount of water involved in the motion is similar to amount of ice.
Yeah. Over here. That one. Yeah. Yeah.
So then it should be okay.
Yeah.
Sorry.
No. It's small. It's for sure smaller than one. For sure smaller than one. Yeah.
I'm afraid I have to interrupt your discussion and we have to move on to the next talk. The next talk is by Evgeny Yaksenov.